Right. Okay, so our first speaker today is Jonathan Mattingly. Jonathan Mattingly is a professor at University of Duke, and he will talk about Gaussian structure of stochastic burgers and related problems. Please, Jonathan.
Thanks, Oleg. Thank you to all the organizers for putting together this nice meeting, and doing their best, even though we couldn't all be together like we used to. But I hope we will be soon. So I want to tell you about a work that's been kind of going on for a while, but has picked up steam. This particular version is mainly joint work with Marco Romito and Longxuan Su. Marco's in Pisa and Longxuan's here. He's a graduate student here at Duke. And this version of it started maybe 6 years ago when Marco and I were in MSRI. But a lot of this was based on previous work with Tufik Soudan. I mean, it builds on it. This is not based on that. It builds on it. And a thesis of Andrea Watkins Hairston from 2010. All right. So when we think about SDs and finite dimensions, we all know that they're intimately connected with a diffusion operator, with a PDE. And somehow the fact that diffusions are elliptic or hypoelliptic, and that they have some density with respect to Lebesgue measure is somehow central to so many things that we do in finite dimensions. It's kind of central to many of our arguments, and that's the difference between an ODE and a PD. An ODE, there's only one topology in Rn, and in R infinity, there's infinitely many different topologies. And that's part of what makes PDs fundamentally different than ODs. There's no one existence uniqueness theorem for all PDs. It changes from PD to PD. So, ellipticity gives you the existence of a density. It fixes that regular topology in a way. And you can kind of think about it as being that this quadratic form formed out of the noise is non-degenerate. That is to say, it's bounded below and usually above for simplicity, but really most importantly, bounded below as a matrix, as an operator, as a positive definite operator by some multiple of the identity, where A here is just, A was D. Sorry, I changed notation halfway through. That's my fault. All right, so in infinite dimensions, there's no privileged topology. There's no universal candidate to write densities relative to. It's not to say that, I'm a dynamicist, so I like the dynamical, the SD point of view, the SPD point of view, but still it's useful to know, to have that topology in the background for many arguments. So I want to kind of briefly touch on 3 examples. The 2D Navier-Stokes equation on the torus, let's say, 1D burgers, again, on the torus with no mean flow or Dirichlet boundary conditions, and 2D reaction diffusion. I'm not going to be so precise about the settings. I don't have a lot of time, but let's just think about these 3 equations, okay? All right, these equations have quite different behavior. So here I have some real values. So this is some basis. You can just think of it as Fourier basis if you want. That's convenient. That's usually what I'm thinking about. But and then I have some real numbers, some coefficients here, and these are standard Brownian motions, okay? Collection. So this is kind of a covariance operator times a cylindrical Brownian motion, if you will. And if this is very rough, so if P is very small, like a positive P and something like this, then we're in the domain typically of singular PDs, as we've come to call it, very rough PDs. If it's algebraically decaying and P is, let's say, much bigger than 1, although I'm not really worrying about the threshold, it's just smooth enough. And we're going to see that things are actually often quite nice. And there is some kind of natural idea of ellipticity. But if things are too smooth, they're actually no longer act elliptic. I would conjecture that typically we should think of these more as hypoelliptic if they're too smooth, if they're decaying too fast, okay? So even though it might be non-degenerate, that is every direction in our space in some kind of weak sense has forcing in it, it's still too smooth to behave elliptically. All right, so the kind of beginning point of this is to think about, well, let's think about it. What is the replacement for Lebesgue measure? So there's no Lebesgue measure in infinite dimensions. And the classic kind of the conventional wisdom is the closest thing to Lebesgue is Gaussian measures. There's a lot of reasons for that. It's the closest thing to something being translation invariant. It has a lot of properties that are similar that we like. So, why not compare the solution of our nonlinear SD with the linear SD that's associated? That is to say, so here's some abstract evolution equation that I've written with some nonlinearity, and just delete that nonlinearity and look at the linear equation and compare it to it. So you might want to ask, as measures, are they equivalent, or at least are they absolutely continuous? Now, I'm going to usually just talk about absolute continuity. Equivalence from these methods usually follows when you have something better than local solutions, when you have global solutions, but it requires something a little bit more. All right. So of course, what that means is if you have this kind of absolute continuity, then this transition density has a density, there's some function. So, okay, so this should really be in quotes because I actually didn't write it right. Sorry, I meant to write that as integrals. I must have been late night writing this. So let's put that in quotes. What I really mean, of course, is that the integral of this should be inside the things, obviously. So, but there's some density with respect to the two measures. All right, so let's get off that screen with that horrible typo. All right, so in one dimension, if you think about this reaction diffusion equation, it's pretty well known that in many cases, for reasonable settings, you can actually use Gaussian on path space to prove absolute continuity. And hereby, when I write 0t like this, I mean the law on path space between these two measures, and usually actually equivalence. And the proof uses Gaussian. So this z here, this is of course just a Gaussian measure, which is given by this stochastic convolution. And the basic idea of Gaussian is if you agree on your path so far, then you're sitting at some point at time t in the middle of the interval, let's say, and you want to take a step. And this is our nonlinear equation u, and this is our linear equation z. And maybe the nonlinear equation wants to infinitesimally go in this direction, and the nonlinear equation wants to go in this direction, as you see here. And what we do is we look at the shift between those directions infinitesimally in phase space, in the tangent space, and we absorb them into the drift, okay? Into the noise. So we absorb the infinitesimal difference in the drift into the noise. That's kind of the picture. That's what Gaussian is doing, all right? And then if you do that, then they follow the same trajectory. Okay, that's what Gaussian does. Okay, so it requires the noise not to be too smooth. That's really important, because if the noise is too smooth, you can't absorb the shift. The shift may be too rough to be in the range of the noise, and so then it cannot be absorbed in. And since this is happening infinitesimally, this is really an elliptic statement. This is not, you can't move the noise through the nonlinearity in this simple picture I've given you and perform this. So this doesn't work for Navier-Stokes or for Burgers, or typically for reaction diffusion equations in higher dimensions. This kind of using Gaussian to prove path space equivalence. Okay, in general, when you have Gaussian measures that are either absolutely continuous or either equivalent or singular. And there's two ways they can be singular. They can either be singular, well, I'll get to that in a second, actually. So one of the ways they can be singular is just having the same covariance structure, but just having a rough shift between them. So Gaussian measures always kind of partition R infinity into leaves of absolutely continuous measures. And that's what these are. These are different leaves. And I suspect in a moment, we'll hear about, how you can have a rough shift that leads to some non-absolute continuity, a random rough shift. Now, that's not exactly the setting that I'm thinking of here. I think that's certainly more appropriate for the reaction diffusion. It may be slightly less relevant for Burgers and Navier-Stokes, but that's a kind of an open question, to say that precisely. So let's now go to one-dimensional Burgers equation. So I have the diffusion and the Laplacian. And let's just, for simplicity, although some of the things require this, but that's just probably due, I don't think they really require it. I think it's just due to what we are willing to put up with doing at the moment. Let's make our nonlinearity be a cylindrical Brownian motion written in the Fourier basis, for instance, with a covariance operator, which is this positive operator. So minus the Laplacian to some fractional power, just defined spectrally. And if we make this a smoothing operator, that is to say, make alpha negative, then actually, I guess this shouldn't be there. That -1 shouldn't be there. But think of it as being smoothing. In fact, if you want to think of it being very negative, then you can use something which I'm going to explain in a second called time-shifted Gersanov to prove that the law of U is absolutely continuous with respect to, is absolutely continuous with the law of Z. But notice I'm only saying at time t. That's really important. So I'm no longer trying to make absolute continuity in path space. I'm only going to say it at a time t, okay? And this kind of method, which we now are calling time-shifted Gersana, goes back at least to some papers of Tufik Sweden and I around 2005 and 2008 for Burgers, I think. And I mean, it certainly is informed by ideas from stochastic analysis, like the Bismuth-Elworthy-Lee formula and ideas like that. All right. So the idea of the time-shifted Gersanov is the following. So now we have the same kind of picture. I've just drawn them on top of each other. We have a trajectory, and maybe this is the trajectory of our linear equation Z. All right. And what we're going to do is we have a direction that the nonlinear equation would like to push us, and we have a direction that the linear equation would like to push us. Of course, it should be tangent to this curve, but I just do it like this for pictorial purposes. And so there's some shift that we'd like, but the point is that shift is too rough to be absorbed into the noise as it is. But since this is a linear equations are, a forced linear equation by the variation of constants formula, by Duhamel's principle, is just the superposition of all the infinitesimal kicks at every moment of time shifted forward by the Jacobi flow to the final time and then added up, right? That's what linear superposition of linear equations means. So we're free to take this shift and shift it forward by the linear flow to a later time, let's say halfway to the end time, t plus s over 2. And by shifting it forward half the way by the linear flow, we get a smoothing, because this linearization is a smoothing flow. It smooths in space. So this shift now is smoother, and it turns out that for Burger's equation, it now becomes an immiscible shift, and we can now shift it into the noise, okay? So by shifting this forward, we use the dynamic smoothing of the equation to actually regularize this shift, all right? Okay, so time-shifted Gersanov. It works for Burgers, with algebraic decaying here and covariance and alpha less than 1/2, and it works for 2D Navier-Stokes if you add any hyperviscosity. So that is to say that you replace the Laplacian in the equation with Laplacian plus 1 plus epsilon, where of course I mean minus Laplacian, okay, just to find spectrally enough. And all you really need is just that it's negative, that alpha is negative enough to have classical solutions. So I'm really not thinking about the singular case yet, all right? So this works for this, and these are old papers by Tufik Sweden and myself. Okay, so can we push this a bit farther? Can we get to Navier-Stokes, real Navier-Stokes, which seems to be just at the boundary, right? Any hyperviscosity is enough to make it true. Or get it closer to KPZ. So to a more singular PD. So today I'm going to talk about the more singular case. Whoops. So here's, so 1D Burgers. So in this same, I should have, this is a quick talk, so I didn't talk, but De Prato and De Bouche, just a year, it was independent of ours, but theirs published a little before ours. And were using completely different methods, but starting here, these are all kind of using these time-shifted Gersanov. So for alpha less than 1/2, now what I'm going to really tell you just about now is the idea is that you need to go from 1/2 to 1, just shy of 1. Now 1, of course, is KPZ. It's the Burgers equations associated to KPZ. And in that case, you might hope that it's still true because space-time white noise is invariant. Of course, you may also think that that's an algebraic miracle. And if you perturb it a little bit, these methods are very stable under shifting the covariance a little bit. They're not rigid algebraically, where kind of strict invariance can be rigid algebraically. And so you might wonder whether it holds at KPZ. And that's still open, though I think we're getting closer to having something to say about some examples like that, but not yet. All right, so what's the idea? The idea is to decompose our solution into a sequence of increasing regularity. Okay, and some other associated work which are in progress, we do it decreasing regularity, so that's not really important, but we're going to kind of factor our solution into a whole bunch of solutions of different regularity. And the way we do that, I think, is part of the interesting thing of this paper. And of course, in PD literature, the Fourier analytic groups going, Chemin, Gallagher, Planchon, others, many others, use these idea of factoring solutions into more and less regular parts. And somehow the old De Prato and Zabchik trick, and I don't know, we should ask them who did it first, of subtracting off the stochastic convolution in a way does that, but it has, I think that's how we look at it now for SPDs. But I think originally as much had to do with just removing the stochastic part from the nonlinear equation. But anyway, so I'm going to write a bunch of solutions like this and have some remainder term at the end, okay? And the idea is that this will be increasing smoothness, okay? So I'm going to start by decomposing the noise. So I have this covariance operator Q, and I'm going to write it as a sum of a whole bunch of positive difference covariance operators, 1 through n, which are going to correspond to each of these equations. Whoops. And then 1 for the remainder equation. Okay. And so if I do that, and I should say, I just to kind of make it clear to everyone, each of these covariance operators is going to be a positive some power of the Laplacian, of minus the Laplacian. And I'm going to have this sequence of alphas that are decreasing. That are decreasing. So that means it's getting smoother and smoother and smoother. All right. And an important fact is, you remember when I told you that time shifted Gersanov worked less than 1/2. It's important that the last in this chain essentially is moving us down into the space where we have nice classical objects. We're getting out of this singular. This is the area where things are singular in the sense of Hare and Gubinelli and De Prato and de Bouche, but we're going to move down to this range. Okay, so we're going to need a number of levels n so that the alpha that our original equation was forced with, that is to say, the regularity of this, is less than 2n plus 1, 2n plus 2. And of course, that converges to 1, so we can't get up to 1 with this argument. And that's what sets the number of levels that we need, however, as we approach the KPZ nonlinearity. All right. Okay, so just for compactness of notation, I'm going to adopt what's often done in singular PDs, which is write this time derivative minus the generator of the Ornstein-Uhlenbeck process that says, well, of the heat flow associated with it as L. And now my first equation in this hierarchy is just going to be the straight up Gaussian convolution with the roughest noise that I have. Remember, this is rougher. The next one will be that equation forced by this, forced by the previous level. And then I'm going to kind of do finite difference derivatives going up, keeping track of each of these. Okay, going down, 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 all the way to the last one, where then I just write down what the remainder equation is. And the point is that if I write this out, if I add these all up, so let me just make some notation. When I write two indices up here, I'm summing up all the levels up from 0 to k, okay? And now, if I write the equation for the nth order without the remainder, it actually looks very close to the original equation, right? It looks very close to the original equation. This is just my nonlinearity for Burgers, if I didn't say that before, sorry. The only thing that's off is these indices are a little off. And the remainder just turns it into exactly the right equation, because I designed these noise, the sum of these noise, to have the same distribution as my original forcing. And this, the sum of these processes, just solves the equation by inspection. I mean, you have to show some things, but that's true. All right, now the idea is we're going to simultaneously compare this with the associated decomposition of the linear process. We're going to decompose it into a ladder of solutions Z. And in the same way, we're going to prove that the sum of all of these is equivalent to the sum of absolutely continuous. The sum of all of these is absolutely continuous with respect to the sum of all of these. Okay. And the way we're going to do that is you see there's a natural kind of feed-forwardness. There's both there's an adaptedness in regularity scale, if you will. Each level depends only on the noise from above. So if we define a filtration like this, which this is the time parameter and this is kind of the scale parameter, we have this filtration in this two-dimensional space now of time and regularity. Then what we'll end up proving is that this law of this variable conditioned on the previous level's noise is equivalent to that the Gaussian at that level. And then finally, the remainder one is absolutely continuous with respect to the last one. The reason that we can only prove absolute continuity here is you see there's this tau, which is the existence time of the solution. Of course, once we leave kind of the classical regularity for burgers, we only have local existence. So we don't have global. So we have to prove this for solutions that only exist up to a random time. Okay, so what we actually prove, I should say, and I was a little sloppy about this, we actually prove absolute continuity up when you condition on it and not having blown up by time t. Okay, and you can fix that just by extending the process to add a death state. And then what I said is true. Like at the time that it blows up, you just need to send it to a death state. Okay, all right. So I think, so let me just pause for a second. If there are questions, I guess I'd be happy to have them, but maybe I should wait till the end, given that I don't have that much time. But the idea is that, we're going to, this decomposition, we get increasingly regular equations. That's to say, this equation from the point of singular PDs has essentially regular terms in it by the time we get down here. So we're peeling off little by little the irregular parts of the solution. All right. Now, of course, if that's true, if that equation is absolutely continuous with respect to the Gaussian, it might make sense. It's not immediate because we're only proving equivalence at time t now in path space, that we could replace this Gaussian, we could replace the x's before with the Gaussian process as before. And we actually, in fact, prove that also. We prove this first and then use it to prove the other one. We prove that for each of these Gaussian, if you instead build the exact same construction, except instead of putting x here, put the Gaussian at that level, then we can prove the exact same equivalence. And this has a lot more. This makes the connections with ideas of kind of tree Ito Duhamel expansions, right? These tree diagrams much more explicit because you see those type of terms exactly coming up in this expansion. So you start to see the development of the singular PD expansion here in this decomposition. The one thing we're doing though is we're kind of keeping noise here, and but we're regularizing it, which I think is different. We're regularizing it as we go down this tree so that we get smoother and smoother equations as we go down these levels. All right. Okay. So we use a mixture of Cameron-Martin and this time-shifted Gersanov. We do have to renormalize solutions up in the higher parts of this decomposition in the sense of Hare, Gubinelli, and the Prato de Bush. And we can usually prove equivalence if we're in a setting where we had global solutions. I'm not going to try to state a general theorem there, but that's the kind of rule of thumb that we see. All right. So let's see. How am I doing? Oh, I'm just zipping along. So maybe it's.
You have around 10 minutes, maybe even a bit more, 12.
Yeah. So maybe it's a moment to ask if there are any questions. If anyone wants to ask a question right now on this. So let me just kind of, while I wait to see if anyone has one, let me just kind of reiterate what we did. Was we took this decomposition, we built this decomposition out of this feed forward kind of finite difference moving forward, and we then showed that this law level by level satisfies this absolute continuity relationship. Okay, and you really can view these kind of as finite differences. And then if this is true at level by level, if these are equivalent, you might think, well, then I could just replace this x with the z at that level. And if you do that, you still get an expansion that works. Now I've just replaced each of the x's with the z's, all right, at that level, and you get a different expansion. And you have, of course, a different remainder term because it's now these. And this really makes much more explicit the connection with the ideas from, formal diagram expansions, okay? All right, so now I'm going to step back and just say a word or two. I could have maybe said more. I didn't think I would have time, but I didn't prepare for it. And it's actually very much work in progress. So I don't have a theorem to state, but I want to kind of think more explicitly about this decomposition across scale. And this is work in progress, but I'm pretty confident we'll have some theorem very soon. I just don't know exactly, and I'm not ready to quite state exactly what I think the theorem is. All right, so let's step back and take a cylindrical Brownian motion by some covariance operator, and let's put a scalar square root of lambda in front. Let's rescale that. So here we have that as written kind of in the cylindrical Brownian motion expansion. And now let's rewrite this, taking the scale in. Let's rewrite each of these real one-dimensional standard Brownian motions. Let's rewrite it as a two-dimensional Gaussian, as a double integral, 1 over time, 1 over scale of a Brownian sheet. Okay, as a Gaussian, or more importantly, I would say it more as a two-dimensional Gaussian measure. So this is a white noise measure on 0 infinity squared. So lambda is the scale parameter. And this kind of expansion using these kind of Brownian sheets, these kind of Gaussian modes are very much, Akita and Walsh. These are the ideas how they tended to formulate SPDs. And Sakai, in the early days of Maluvan calculus, has some very nice papers where he kind of explores different types of Maluvan derivatives. And he actually discusses a Maluvan derivative with respect to scale, which is somehow implicit in the background of what I'm doing, is kind of a derivative with respect to scale. And so the idea then would be is that you start with the scale. So this is, should have said lambda. So the scale equals 0. And if you do that, you just have the deterministic heat semigroup, and you end up at some point. And then you slowly turn the noise on. And as you slowly turn the noise on, there's some collection of directions that one equation wants to go and some collection of directions that the other equation wants to go. And if those infinitesimal measures, which are actually the Gaussian measure in that tangent space is given by the Maluvan covariance matrix, if those are infinitesimally equivalent, then you can absorb one into the other and slowly turn the noise on and kind of homotopy to the true solution. All right. And so, like I said, this is work in progress, but it really is the work we did before can really be understood that way. Okay, that's what's really going on there. All right, so let me just maybe summarize what we've answered and some questions that are raised by those answers. All right, so we've shown absolute continuity for alpha just less than Burgers, just less than KPZ, or with respect to the Gaussian measure. So we've shown that there is a natural Gaussian measure. And so, and KPZ seems to be the endpoint of these methods. So there's a natural question, does it work for the endpoint? Similarly, if we add a little bit of extra smoothing to the Navier-Stokes equation, if we make it hyperviscous, then any kind of algebraically decaying, and if you have classical solutions, then these methods also apply and give you absolute continuity with respect to the actually equivalence, because you have global solutions, with respect to the Gaussian measure. But what about the Navier-Stokes equation? It's again the endpoint. And tantalizing, it's interesting to notice that both of these equations at the endpoint, because they're critically scaled, both cases are the cases that have space-time white noise invariant. And so these methods would let us answer the question about what about nearby Q? What if we have a Q that has has asymptotically equivalent topology, but is not just the Laplacian to the right power? Would that still have a transition measure absolutely continuous with respect to the space-time white noise? Okay, that's not known. And then what about non-degenerate? What about smoother but non-degenerate forcing? I would conjecture that, and this is nothing new. I think many people think this way. I would conjecture that that's morally equivalent to a hypoelliptic diffusion in nature, even though because it forces every direction in the Sobolev space, but it does so in a way that decays so fast to make it very smooth, it really should be thought of as a hypoelliptic diffusion. All right. And with that, I'll just say thank you, and I'll be happy to take any questions anyone has.
Okay, so thank you very much, Jonathan, for an excellent talk. So I would suggest that we will now pass the screen to Nikolai, and then in the end, we'll have questions to both of you. So could you please stop sharing and we ask Nikolai to start sharing?
Sorry.
Nikolai, can you unmute yourself, or
Yes, sorry.
are you okay? Yes, very good. We can see you.
So wait a moment. So can you see the presentation?
Yes, you might want to do full screen or not, whatever you want.
To go, like, I'm on a different computer than I'm usually am because the Zoom doesn't work on the other one, so I have to.
Okay, so meanwhile, I can say that so we have now a discussion by Nikolai Barashkov. Nikolai is a PhD student at University of Bonn, and he works
Postdoc.
there.
Postdoc.
Sorry, congratulations. We can all congratulate Nikolai with his defense. And I can say that when Nikolai was a PhD student, he was working with Gubinelli, and with whom he was working now, I don't know. But anyway, Nicholas, the floor is yours. So please begin.
Thank you, Oleg, for the nice introduction. So yeah, let's start with the discussion. Yeah, okay, now it works. So yeah, so we want to, let me just, maybe let's just summarize what Jonathan said already. So like I said, we might say the same thing twice, but that's usually not a bad thing. And so, okay, we have this kind of Burgers equation where we have a heat equation here. So A is the Laplacian. And then we have some nonlinearity, which is the derivative of the square. And then, okay, we have space-time white noise, which we derive to make it more, make it rougher. And okay, we put some initial condition. And then, okay, in for delta equal 1, we have this derivative here. So it's kind of like the KPZ equation, the derivative of the KPZ equation. And we want to study transition probabilities. So you take this equation, you run you run it, and then you see you look at what is the law after this time, and this gives you your transition semigroup. So there should be a T here. Sorry. And then okay, the question is, what about absolute continuity with respect to the same equation for the linear, the same transition probabilities for the linear equation? This is, I guess, the central object of the paper, of the recent paper of Jonathan. And okay, the idea is to decompose the noise into different parts with increasing level of smoothness here. So you make the Q kind of better. And then here you feed this noise through these different nonlinearities. But the point is that at each level, like these equations are all linear, and only the last one is nonlinear. And so to each of these equations, you have a shift which is nonlinearly dependent on the previous noises, but is independent of the new one. And so you can apply Cameron-Martin to each of those to get absolute continuity with respect to the free field. So yeah, and then to the last one, you kind of have to use Kirsanov theorem, because here you really have a nonlinear equation. So you're forced to use Kirsanov. And okay, maybe let's skip this in the interest of time for now. And then the result is you want to prove at every level of decomposition, you want to prove that the law of the solution for all of these is absolutely continuous with respect to the solutions of the linear equations, where the linear equations are defined in the same way, but you don't have those nonlinearities here. And from this, you can infer absolute continuity for the whole sum. And the tools are a modified version of Kirsanov's theorem, which Jonathan introduced with his collaborators, and the Cameron-Martin theorem, as I already mentioned. So this modified version of Kirsanov's theorem is kind of like, you take the normal Kirsanov theorem, and then instead of directly applying it to the equation, you modify the equation. So then you fix a time big T, and you construct a new equation which at time big T has the same solution as the previous one. But now this drift will be better. So you kind of get an additional smoothing from the semigroup. here. And this, you can do this computation. It's like a change of variables. And the point is that this really, you get this shift, which is now better behaved due to smoothing. But the trade-off is that you've modified the equation, so it's only equal to the original solution at time big T, so at a fixed time. So for every time you fix a time, you do Gaussian, then you get absolute continuity for the fixed time, but you don't get it on path space. Whereas if you do normal Gaussian, of course, you get absolute continuity on path space. And so, okay, then you can compare this kind of things. The shifted Gaussian time shift, Jonathan calls this a time shifted Gaussian theorem, and you can compare it with the Cameron-Martin theorem, and you see that the regularity requirements are mostly the same, but you have a trade-off in the sense that in space the regularity is mostly the same. So this requires, if you look at this, then you see that this gives you you get a semi-group more here. So this kind of gives you a +1, and then you look at this equation and you see that it's the regularity in space is the same, but the regularity in time here is less strict because you can have this F be a space-time distribution, and here you need it to be pointwise defined time. So for some of these equations, you actually don't have, this is like something which happens in KPZ or in 543, that you don't actually have space-time, you don't have something which is fixed in time, a distribution which you can restrict to some time, you have some space-time distributions. And okay, the advantage, this is what I wrote here. And okay, of course, the advantage of Gaussian means that you don't need the Cameron-Martin is something which requires deterministic drifts or is something which are independent. And the advantage of Gaussian is, of course, that you don't need this. Okay, and kind of where does this decomposition sort of come from? So why do you want to introduce it? Well, it's sort of imposed upon you by the different regularities of what you want to do. In the sense that you want to have, you have this shift here, and you want to prove absolute continuity with respect to the law of this noise. And then you do a computation, you expect that the rough, a lot of parts of these things here, so you take x0 and -1, which is the sum of all these x's, which solve all these equations up to level n. And you subtract the level under it, and then this is bilinear. So what you're left with is basically this term plus terms which have more higher i's. So since the noise here is smoother, they're sort of smoother. And then you do the computation, and you see that the regularity for this should be 1 minus alpha 0 minus alpha a minus 1. Well, the alpha I is how much you have roughed the noise, sort of. And then the Cameron-Martin condition gives you that alpha I, which is the regularity of the new noise, should be bigger than alpha 0 plus alpha I minus 1 minus 1. And on the other hand, in the final step, you want things to be classically defined. So you want alpha n to be sort of less than 1/2 for the final noise not to be too rough. So you can actually solve the equation for the remainder. And so if you do the induction on this condition, so you iterate it a lot of times, and then you get that alpha n has to be bigger than n plus 1 times alpha 0 minus n, which implies that alpha has to be less than 2n plus 1 over 2n plus 2. So the computation works if alpha is less than 1, and the closer alpha is to 1, the bigger n needs to be. So the more levels you need here in this decomposition. So this is the reason you need this kind of general decomposition, and you can't just quit after like one step, because it's really imposed upon you by these regularities. And okay, so maybe some more general context is, so it's this is kind of closely related to the notion of regularity of a semigroup. So if you have T0 regular semigroup, if after time, if you pick two initial conditions and you run the equation, and after time T0, you have the laws being equivalent. And regularity of the semigroup implies uniqueness of the invariant measure if it exists, but usually it exists. And mixing, which means you have convergence to the invariant measure. And there's a theorem which is, I don't remember how it's called. It means that the Strong-Feller property plus irreducibility implies regularity. But yeah, maybe sometimes the regularity, Strong-Feller is actually not so easy to prove. So maybe this is like, it's a nice way to prove these directly. And okay, then maybe some more general context even. So there's many different results for different equations on mixing. For Navier-Stokes, Daprato-Dubuche, Hyra, Mattingly, Bricmont, Copiainen, and Lefebvre have a paper, and also Flandolé and Romito. And yeah, for the nonlinear cubic Schrödinger equation, Dubuche, Bruto, and Dubuche and Odasso have a paper where they use, of course, they have to use smooth noise because the Schrödinger equation doesn't actually regularize. And then for wave, Tolomeo and Forlano have something. And then there is, of course, the stochastic quantization equations, which is heat equation plus a nonlinearity equals to noise. And with this being a cube, there is a lot of results on stationary solutions in 3 dimensions, in 2 dimensions. In 3 dimensions, there is a paper by Bavaria and Kozolka and Gubinelli and Hochmanova in the whole space. And Satsoulis and Weber have proven exponential convergence to equilibrium on a torus in 2 dimensions. It would be actually quite interesting to see if this kind of thing can be done in 3 dimensions. But this seems quite difficult. And then Bauer-Schmidt and Boudinot actually proved the log-Sobolev inequality for the sine-Gordon equation, so where you take V to be the cosinus. And this will imply exponential convergence to equilibrium. Okay, so yeah, and the other way is sort of the other perspective on this kind of thing is that since Jonathan proved absolute continuity with respect to the linear equation, it sort of gives you a way to transfer pathwise properties from the linear equation to the nonlinear equation. And this kind of thing is also quite common in other problems. So for the equilibrium, it's of course known that, for example, in 2 dimensions, in finite volume, the sine-Gordon and the 502 measures are, or P502 measures are equivalent to the Gaussian free field. And this has found many applications in dispersive PDEs. So when you want to construct an invariant measure, which is invariant under a flow of a dispersive PDE, like, for example, nonlinear wave with cubic nonlinearity, then you kind of want the non-Gaussianity because, of course, you want to have the measure to be invariant. But then usually these measures have support, which is below the local well-posedness theory for the equation. So you need to prove, you need really to use the Gaussian structure of the measure to prove a local well-posedness. And then you have to combine these two to actually get the invariance. And so for this, you kind of need to transfer the Gaussian structure to the non-Gaussian object, which can be done with via absolute continuity. But okay, the other way is to replace give us some sort of replacement for absolute continuity is to construct a coupling like this. So you take the non-Gaussian object and you decompose it as a part which has Gaussian law and something which is more regular. So for example, this was what we did with Massimiliano. And then Björn Brinkmann used this to actually apply this for dispersive PDEs. So we constructed, we took 503 and we wrote it as a absolute continuous perturbation of the Gaussian free field plus a Wick cube of the Gaussian free field, but smooth, so something which has Hölder regularity 1/2 minus, so relatively nice thing, and plus some remainder, which is even better. And then Björn Brinkmann actually used this kind of thing to do local opposeness for the nonlinear Hartree wave equation, where okay, he wasn't able quite to do cubic nonlinearity in 3 dimensions, but he has to put a little bit of smoothing. But okay, it's almost there. And then there is this nice work by Bauer-Schmidt and Hofstetter, where they actually have a similar result. So they have a coupling of the sine-Gordon measure, which is the invariant measure for this equation where you put the cosine, with an object which is not necessarily in the Cameron-Martin space, because they cover a range where the sine-Gordon model is singular with respect to the free field, but it is still pretty regular. And actually it's L-infinity even in the probability space, so it's uniformly bounded, which is sort of related to the fact that, okay, if you take V to be the sinus, before you normalize, it's bounded. So this is something which they use heavily. And this, they can use this to study the maximum of the sine-Gordon model on a lattice. So they take a lattice with mesh size epsilon, and then they take the maximum of the field. They take the field which is distributed according to this law. So we would say, for example, you could run this equation up to time infinity and see, then you get some object on the lattice. So you regularize this equation by going on the lattice, you run it up to time infinity, you get something. You ask what is the maximum. And then they are able to prove that if they can subtract some deterministic logarithmic corrections, they can determine the distribution of the maximum as the mesh size goes to 0. And this is really due to this kind of coupling, because you can transfer these pathwise properties. Like you can transfer the strong control you have over the Gaussian object, and then the non-Gaussian control is also very strong, because as I said, it's at infinity in the probability space. So yeah, I think okay, I can come to some questions for Jeremy. So what kind of equations can you do this for? Like, do you really need the heat? Like, do they need to be heat type equations, or like parabolic equations, or can you do this for wave or for something else? And can you do something where you expect like singularity with respect to the singular PDE, with a singularity with respect to the linear equation, if you modify the linear equation? So let's say you take 543, you add a cube, like you take the linear, the Ornstein-Uhlenbeck equation, and you add like a Wick cube to the right hand side or something. Maybe you could hope to get something where you can prove a similar result to what you did. And if so, can one construct couplings of these objects and transfer some kind of pathwise properties? So yeah, I think I stop here. Thank you.
Thank you very much, Nikolai, for your very, very nice discussions and for explaining us Jonathan's work. So Jonathan, do you want to answer some of these questions?
Sure. And I should also say that Nikolai was very modest. He didn't spend much time talking about his own work and explaining his nice paper with Maximiliano. So you should also go look at that about exactly this kind of thing where in some of these equations, you actually don't have absolute continuity with respect to the Gaussian. So that's what their paper is about. Is that fair, Nikolai? Yeah.
Yeah.
Yeah. So he was very modest. So I'll plug his paper for him. I think so. A few answers to your questions. So you brought up a good point, which actually I usually talk in a longer talk I would talk about, but I didn't. So the connection with Strong-Feller, right? I mean, that's very much what's going on, right? The way you often prove Strong-Feller is by something like a Bismuth-Elworthy-Lee formula or something like that, or the modification of it that like Martin and I used for KPZ when we proved Strong-Feller of that, which is kind of a pathwise version of that. And that very much requires this exact picture of infinitesimally in the tangent space having absolute continuity of the directions that both equations want to go. So it's very related, those ideas, right? Other equations. So, I think the way we've done this, so of course, if you can use Gersanov, then you're great, right? But when you can't use Gersanov, then you need something to make it more regular. So it'd be a question of if you went to a wave equation, could you do some kind of time shifting? Is that kind of moving in space time enough to regularize in some sense via some Strickhardt estimate or something, right? And that's not enough my jam, my domain of expertise to be able to answer that well. So, and the last question, it's very much true. I mean, that's exactly what we're working on, right? We're working on, well, what are the interesting cases? There's these two tantalizing boundary cases, which are two of the equations we care a lot about, Navier-Stokes and KPZ burgers are the two boundary cases. But there's also just more generally, what about Navier-Stokes? I mean, what about Navier-Stokes in general? What should it be absolutely continuous with respect to? Or should we add in some extra terms? What's the kind of minimum terms we need to add in to keep absolute continuity? That's kind of, this is, a step in that program, hopefully. But there's lots of interesting questions. And I'll point out one other interesting thing. First is in Andrea Harrison's thesis, you very much is kind of using equivalence to prove ergodicity and statements like that was in there. And that was kind of the original motivation because we were not thinking about singular PDs at the time back in 2010. But then Marco Romito has a nice paper where he does exactly this kind of question where he says, well, you might be interested in the pathwise properties at time t of the solution. I can calculate them for the Gaussian. So by using this absolute continuity, I can transfer that to a simple Gaussian question. So like, for instance, in fluid mechanics, a lot of times people are interested in what's the Hausdorff dimension of the level sets of the velocity of the vorticity field, or does it behave like SLE something or another? I forgot which one. And of course, if you do have this absolute continuity, you can transfer that to a question about the Gaussian measure, which you have hope in the free field where you actually have hope of proving such a thing, right? So that was my motivation in the very beginning, was actually being able to say statements that, and also point out that maybe these weren't really good models for turbulence in some ways, because they just were at the small scales, the linear behavior dominated. So they don't make the best models in some ways, right? Anyway. Thanks, that was great.
Okay.
Should have had you give my talk.
Okay, so are there any questions from the audience? We have time for maybe 2-3 questions.
Cool. Hello? Yeah.
Yeah, hello. Please continue.
Hey, Shumei.
Yeah. Hey, Jonathan. It's really nice idea, very nice talk. I was thinking about when you're talking about the technical aspect of your talk. When you do incremental smoothing through this absolute continuous systems, I would expect you have some quantitative estimates. You might even need that to reach your last step.
Yeah, very much so. I mean, so Nikolai kind of gave, so is there more to the question, Shumei? Sorry, I didn't mean to cut you off. Is that it?
The question is, do you see the quantitative estimate decays at a certain rate as we expand?
Can you say more about, so let me give you the short answer, and then my follow-up question to you is, can you say more about what you mean by rate and what you might expect? So the short answer before letting you specify the question more is that, yeah, I mean, we find that the increment that we can smooth, actually, as we're or trying to reach something at the endpoint, that little increment has to be smaller and smaller and smaller. And that's why the levels have to get bigger and bigger and bigger, because there's exactly this kind of balancing, right? And in fact, what we're working on now is actually a version which is in some sense continuous. So it's no longer incremental, right? It's actually the continuous version of that. And that's what's in progress. I hoped I would actually be able to talk about it, but we don't really have a theorem yet. We have lots of calculations, which we just need to decide what the theorem should be. Nice to see you. Do you want to say more about what you mean by rate, or is that answer the question?
It does. I was thinking about the density itself.
Yeah. So you get a formula for density, which is interesting. Actually, you actually explicit in this is there's a formula in the background for a constructive process for building the density. Yeah.
Then maybe you could obtain estimate for the gradient of logarithm a short time. Maybe that sort of thing would give a good quantitative control of what you're looking for.
Yeah, I haven't tried that exactly. I mean, I've used the second variation of the Maillard derivative, which is not unrelated to what you're saying, right? So kind of the second variation of the Jacobi field, right? Or maybe
right.
Jacobi field, yeah. So I in another work that's in progress, we're using that, but I haven't used it quite in the way you're saying, and at least not, I can't real time recognize the connection between the two. There may be one, but that's an interesting question, Shumei. Thanks. Maybe we should talk. That'd be interesting. We should talk anyway. It's nice to see.
Yeah, we should talk sometime.
Yeah.
Thank you.
And I did, by the way, now that Shumei's in front of me, I didn't know she was here, but I did say very clearly, I mean, like these ideas kind of shifting forward, that's really that's really one of the key insights in the Bismuth-Elworthy-Lee formula. That's very much in there, at least how I understand it. She may understand it differently, but that's my understanding.
That's rather standard.
Yeah.
Okay, thank you very much, Shumei. Are there any other questions in the audience?
So I had a question. Is this decomposition that you do to get the absolute continuity, is there any hope of using this to understand the Rideau-Nikodym derivative to say something about the distribution, or is it really pretty qualitative?
No, we're actually building a Rideau-Nikodym derivative. So this ladder gives you a Rideau-Nikodym derivative built in. The paper builds a Rideau-Nikodym derivative. It's not like a formula for it, right? It's not an answer in the 19th century sense. Like here's the formula. It's an answer in the, you take these, it's Cameron-Martin, right? So you build up a product of Cameron-Martin terms, which is the Rideau-Nikodym derivative. Did I answer your question kind of, Alex, or is that?
Well, I guess I was just asking, is it explicit enough that you could start saying things about, if you had some properties you wanted to prove about it?
Yeah, I think so. But it's built out of a ladder of kind of adapted Gaussian processes, right?
Right. Okay. So then maybe you could actually analyze it.
Yeah. So you have some hope because the Gaussian processes, you in theory should be able to know anything you want about them, right? Any question should have an answer. And then you could try to build it up, right? Yeah. Except for in this version, the very last term, there's this remainder, which is this. Nikolai did a very good job. I cut that out because I was worried about time. But Nikolai kind of intuited that I left it out and just put it back in, which was wonderful. Thank you, Nikolai. But this idea of this last term is nonlinear, right? So there is maybe the sticky wicket, but it can be made negligible, probably.
Okay, thanks.
Okay, are there any more questions? Okay, if not, that I have a quick question. So what about, so we now learned from Nikolai that, so if from his explanation of your work, so if this alpha was less than 1, then indeed you have a finitely many guys, and then this process will terminate at some point. So do you have any hopes for KPZ when you have infinitely many guys?
Yeah, that's a version of what we're working on right now. Right now we're working on the version where you do that infinitesimally, and we're making progress, but if I had a precise theorem to state, I would state it right now, But
you would expect the same result, the same absolute continuity?
Oh, today I do. I will be honest and say that if you listen to a talk I gave probably a couple months ago, I would have said right now I don't expect it. So, you know, I've changed tunes, but right now I actually think I might, I don't know, actually. Navier-Stokes, I don't know. It's a good question. It's a question that I'm actively interested in.
Okay, sorry, and then a second quick question. So, and this is also was mentioned by Nikolai. So you use this to prove that the protest will be in the end Strong-Feller, and then you expect the KPZ to be Strong-Feller?
So we didn't prove Strong-Feller using this. I mean, this KPZ is Strong-Feller. Martin and I proved a theorem that says that. Right, and so that's not that. I mean, there's some similarity in some of the ideas there, although different.
Okay.
Yeah. Yeah. I mean, so KPZ, and so is Navier-Stokes, right? Navier-Stokes is Strong-Feller. That goes back, you know, to Falun-Dohle and Maslovsky, at least. And so you already know that for KPZ and for Burgers, I mean, for KPZ and for Navier-Stokes, if you start by nearby initial conditions, you can probably prove they're absolutely continuous. They're certainly not singular if you start nearby initial conditions.
Right, but I mean, now your noise is a bit smoother, and so still the Strong-Feller property does not disappear.
No, I mean, this proves equivalence. Yeah, I mean, this proves equivalence to the Gaussian measures, and then the Gaussian measures are all equivalent for different initial conditions. So, I mean, yeah. I mean, I didn't quite formulate it as Strong-Feller, but I don't always think the Strong-Feller is the end-all be-all. But certainly, absolute continuity is true, and equivalence of transition densities are true, and continuity in total variation distance is true, right, of the transition densities. So it's a map from initial conditions to measures, right?
Okay, thank you very much. Okay, so then let us all thank very much Jonathan and Nikolai for the great talk and the great explanation. And let us now move on to the talk of Sandra Chirai. Sandra?